difícil encontrar um amor como esse, tão enganado. Então, por favor, não deixe assim morrer. Eu te amo.
Now there's something to tell you. When you wait to find another, and all the world is telling you to go and fill your heart with sorrow. Don't let the doubts disrupt your brother. Keep you from the things you love. Don't stop looking for a lover. This is surely my best advice. And you know I've been there. I've been there, I lost it all, I lost it all. I've lost it all, I lost it all. I've lost it all, I've lost it all. I've lost it all. When your heart's full of trouble, you can't go out and live in hell. It just goes on and on forever. Boy, you got to break that spell. When you wait to love never, see a chance.
So welcome back to the main plenary room, ladies and gentlemen. I trust that the breakout sessions, parallel sessions, were interesting, informative, that you've had some good discussions and networking as well over in the Riverside area. To those of you online joining us, I remind you once again, do keep sharing on social media. Remember to use those hashtags. You can use BAT4EU, BID or BID2022 to share with your colleagues who couldn't make it here today. And of course, just to make everyone feel a little bit more collegial, I'm going to ask for a show of hands in the room at this almost halfway stage. Who's feeling very optimistic about the future? Hands up if you're feeling optimistic. Hands up if you're feeling pessimistic. Okay, good. Only one person. Right. The final stage of today's presentations are going to take the form of 4 specific presentations. We've got 2 remote speakers for you and 2 here in the room. As before, we'll be taking questions from the floor, from the auditorium, as well as from the online audience feeding through. The overarching theme for these 4 presentations is accelerating research to enable the batteries of the future. So I'm going to see if we have joining us online. We should have Ivano Eglio Castelli, who is the Associate Professor at the Technical University of Denmark in the Department of Energy Conversion and Storage. Hello, Ivano. I think we can all see you there. I'm going to hand over to you. Please do. You're going to tell us how handling data can accelerate battery research. So over to you. And in the catchphrase of the last few years, I think, Ivano, you might be on mute.
Yes, I was. So Thanks a lot for inviting me here, and I'm sorry I couldn't be present in the room. I unfortunately had to teach this morning, so I had to go back home. So should I just tell you when to switch slide, actually?
Ivana, I'm not sure if you can see it, but we have your first slide up now.
Yes. Okay, great. Thanks. So yes, I can see that. So what I'm going to talk in the next 15 minutes is how important are data in a large initiative, in particular related with batteries, and taking two specific examples. So starting from what we are doing with Big Map, and then going beyond Big Map, and how do we plan to expand this methodology also to the other Battery 2030 Plus project family, but also by extend also to the European battery network. So if you can go to my next slide. Great. So first of all, I would like to tell a little bit about Big Map. I don't know how much you know about it, but Big Map is a project that was founded a couple of years ago. The full title is Battery Interface Genome Materials Acceleration Platform. As you can see from the name, it's composed of two parts, Big and Map. The big part is focused on understanding and controlling the battery interface. You can say why really the battery interface is because the interface is playing a fundamental role in any battery devices. You can imagine, you can see how many parts of a battery we have. We have a cathode, we have an electrolyte, you have the anode, we have separators, we have current collectors, so on and so forth. And all of those, the understanding those interfaces is fundamental to improve our batteries to understand how that works. And then we have the map part that is instead the artificial intelligence orchestrated process. So basically, our vision is to develop a methodology that is chemistry neutral to accelerate the discovery of battery materials. And how do we do that? Is basically to make these new tools that can enable an automatic data acquisition, automated analysis, experiments or simulations, predict properties, bridge scales, identify descriptors that could help us in improving our materials. So in the figure below, you can see how Big Map is actually encompassing a variety of domains, from modeling, both from atomistic and mesoscopic, continuum to multi-scale modeling, autonomous experiments, autonomous characterization, synthesis robotics, testing, and different levels of deep learning methodologies. So if you go to the next slide, so this is more or less how the project develops. And you can see on the part of the left, we have more like the conventional sort of work package that we've been used to see in the last years. So where we have modeling and the different levels of experiments. And then the central part here is really what is new. So the part of having an infrastructure, having an ontology and standards and protocol. And I'm going to go in the details of this later, because this is really the key point of what I'm going to talk today, and what makes a sort of the strong foundation for the project. And then on the right part, there is the machine learning work, so that gets fed by everything is on the left in order to generate new data, or get the new data and generate new models. And in a sort of a feedback loop, we can imagine that the artificial intelligence, and this is probably what Helge is going to talk later, calls for experiments, calls for simulations, and so on and so forth. But to make sure that this actually works, we need to have to speak all the same language. And the project is composed of 34 partners, industry, academia, large-scale facilities. So the question here is, how do we make sure that the data that we have are really useful? So the data that I produce can be used by Helge, for example, in Germany, and the data that he produced can be used by me without having to, look at one by one, because that is, we are imagining terabytes of data. And we cannot do this. So, and that's actually where having an infrastructure that allows this, having an ontology that connects all the data, and having a data standard so that we know what kind of protocols we need to use is really the fundamental part here. If you go to the next slide. So data, what is data? So normally we are used to think of data as a result of an experiment or a simulation, but data is much more than that. You can see a short list here what can be covered by data. I'm a modeler. So for me also, scripts, input, output, everything is data in that sense, right? I want to make sure that all the protocols that, or the scripts that I write, both for running simulation, but also for analyzing the data, for me, that is important. But also movies, pictures, documents, if you have a lab notebook, that is something that you need to know what kind of experiments you have run and how do you run that. And how do we make sure that we are actually storing all of these huge amount of information that are so diverse? We have a zoo of data in this case, right? And we want to have a line, a red line that connects all the data together. So the way that we did is in the paper that you can see there is developing a data management plan for this. And the central part there was designing these like tables, that the one on the right, where you can see which data are generated in each one of the work package or by partner. And this is important because we don't care of how it's generated, but what is generated, right? So we want to know that we have this set of data. I don't care much about what kind of the details of the specific simulation, but I want to know that in general, what is the input, what is the output, what can I do with that? Because if I know that I also know how other people can be using this. So in this case, I make the example between atomic scale simulation and characterization. You can imagine that characterization measure a spectra of a material, and they don't know what kind of material it is. So then they give me the spectra in a specific format. I do the simulations, and my output is a structure, a composition. And then I can also do the other way. So I design a new material that is currently unknown. People synthesize this, and during the characterization, then they want to check that my computational predictions. So this forms sort of a framework of the flow for the flow of the data. And in the next slide, you can see how actually this is joined all together in the full sort of data flow in the project, right? You can see that we have the infrastructure in the middle that talks with standard ontology, and I'm going to do that in a few seconds. But then we have also the modeling part, we have the synthetic characterization, and we have also artificial intelligence. And we don't forget that, I mean, out there are plenty of repositories with data. And then we want to be able also to retrieve data from there. So this allows us to sort of follow in a general way what are the flow of the data here. But let me tell you a bit more about the infrastructure. So in the top picture on the right, that's our idea of the infrastructure, where you have two different levels of openness. One where it's like fully open for everybody, and one is restricted because we have also commercial partners. Right? We want to make sure that they feel safe to share data with us within the project. And of course, then it will be blocked outside. But how do we interact directly with the infrastructure is through this app store. So different apps that are basically the connection between me as a user and the infrastructure. You can find them in the Big Map App Store. And then the ontology is basically a vocabulary able to tell me what are the different relations between the battery parts, and standards and protocol that tells me how to run an experiment or how to run a simulation. And you can see this at the link here. If you're interested in reading more about the data management on Big Map, you can see this is the paper, and the supplementary material is 120 pages of tables describing how the data are dealt in the project, what is made by each partner or by each work package, and what is the relation between this data and the rest of the project. But now, in the next slide, Big Map is one of the 6 projects of Battery 2030 Plus. How do we make sure that we don't have 6 different infrastructures, we don't have 6 different ontologies, and the ways that we are talking all together to make a common, like a seamless flow of data. And you can see more or less in the right, what we've been doing was asking to each one we have a task force for data in Battery 2030 Plus, and we ask to each one of the project to create the same data tables that I showed you before for Big Map. And that result in several thousand lines of Excel sheet that we scrolled, and we created links between Big Map in the center and the other 5 Battery 2030 Plus projects around it. And I mean, here the role of Big Map is in the center because I'm the data coordinator of Big Map, but in principle, this shouldn't have any center. I mean, data is in the center and all the other projects are around it, right? So now you can see that, for example, simulations could be used also by Eden and Bat Forever, who can feed data also to Spartacus and so on and so forth. So the ambition here is to create really a flow of data starting from Battery 2030 Plus, but we don't forget that we have also other consortia like Battery Europe, BEPA, and so on and so forth. So the ambition here is to really create a data network across Europe. The next slide, please. And then, as I said, we have several thousand lines of Excel sheet, which is impossible to follow by hand, right? I mean, it took me hours to go in and select some of the interesting links that to make that figure, but we want to make an automatic way to do this. We want to make an automatic way that if one partner changes or adds an instrument, everybody gets notified and creates new bridge. And how do we do that? Is basically to create this ontology that is a data model that represent data acknowledgement as a map of concepts and relations. So here we have conventionally the battery ontologies, for example, BAT-info, but then we want to have a data ontology. So telling us what is the relation between the work packages and the tasks and the participants, and creating links like this, the one in light green, right? So you have the full big map, you have the partners, you know which partners is involved in which project and which technique is used in each one of the tasks. And then you connect this with domain ontologies that are already there. And you could actually connect these also with, not only BAT-info, but also other established ontologies like OSMO or MODA or EMMC, EMMO. So basically the data are really in this case, you can follow from the generation of the data through the data ontology and the domain ontologies. And the next slide, I think, is more or less, this is what I wanted to show you. These are my contacts if you have any question or you want to know more. And of course, again, thank you for inviting me here, and thank you for the fundings both within Big Map and Battery 2030 Plus.
Thank you very much indeed, Ivana. You've packed an awful lot into those slides, so we do appreciate that. And of course, we can see there the contact details for those of you who want to look in more detail, because I know there was quite a lot of text on them. Do we have any questions for Ivano from the floor? Let's see any hands there if people want to drill down into some of the points he was making. No? No one at all. Ivano, I think you've actually covered everything. You've done the impossible. You've explained everything we need to know about data and accelerating the research to enable batteries of the future in just about 10 minutes. So thank you very much for that. Do we have any?
You're welcome. If I can just make a wish.
Yes,
please go look in infrastructure and contribute to that. This is really an open source, and we need the data from everybody to be able to accelerate and to raise more hands for the people that are confident that we can achieve this in the future.
Well, thank you very much indeed, Ivano. I'm going to let you go, and we do appreciate you taking the time despite not being able to travel in person. So thank you very much again.
Thanks again. Bye-bye.
Thank you. Our next speaker is also joining us remotely, so it's going to be discussing experimental discovery lines to screen new materials. Another quite dense topic, so I think we're going to probably see quite a lot of slides from Helga Stein as well. Now, Helga, have we got you online? Helga is the tenure track professor for applied electrochemistry at KIT. Helga, we can see your first slide on the screen, and I can see you've joined now remotely, so I'm going to hand over the floor to you. Please do take it away.
Yeah, thank you very much. So Ivano already set the stage for, well, how can we, work collaboratively together by sharing data in using open standards and ontologies. So this is, let's say, the way of how we communicate between projects and between labs. And I'm going to talk a little bit in the following, actually just 5 slides, about what how we actually generate this data and why we actually generate this data. So on the next slide, you could see a little bit of a motivation. So why do we need accelerated discovery? So for me, this essentially exists on 2 lines. So there is the X line, that is essentially the scale on which you produce batteries, and that goes really from the single cell So my group doesn't do that, but there are definitely groups, for instance, here in the building that make, individual cells. And I bet that in the audience there are people that make individual, like even just half cells or so. So this is like all the way on the low end scale. This is why this is logarithmic. And then there are, there's always people looking at, well, maybe my battery technology can eventually translate to something like a gigafactory or even a terawatt factory. But there's one catch, and that catch is pretty important, and that is in research where we do the individual cells, we are extremely agile. Meaning, today I could say, hey, let's try, I don't know, a new chemistry. I could go for a sodium battery. Tomorrow I go for a magnesium battery. That doesn't fundamentally change the way how I operate the lab. And it would take me probably a few days or even weeks. But fundamentally, I don't have to change necessarily how the lab looks like. A gigafactory, if you just change a small thing from, for instance, going from a cylindrical cell to a prismatic cell, that will mean, quite a lot of investment and probably a lot of downtime. So what is in between there are these pilot lines, and these pilot lines are probably something that some of you know. These are the lines that work on the kilo scale, whereas the gigafactories work on a ton scale. Now, what we do in these discovery lines is we try to go not to the microgram scale single battery, but also not yet to the kilo scale. I always call this the almost kilo scale. So the reason is simply a setback, let's say a chemistry that doesn't work, doesn't necessarily cost us years or billions of euros, but probably just a few, dozens of bucks and a few days. So how does this work? How can one build a discovery line, and how is the discovery line actually fundamentally different from a research lab, and what do these materials acceleration platforms have to do with this? So this is what I'm going to discuss in the next slide. So if you operate on a couple of dimensions, so you don't just operate on the axis of like scale and agility, but you also operate on, let's say, throughput, and you either have a focus on the bulk materials, on the interfaces, like Ivano already mentioned, what we do in BigMap, and then of course also on systems. And in a discovery line, you try to merge all these three concepts together. So you're trying to go from materials, the understanding of the interfaces, to the actual systems in a rapid way. And the way to do that is by covering essentially the whole breadth of throughput. So for instance, there are different labs, not just mine, that have combinatorial synthesis. This has been around since essentially the 1990s. You have high-fidelity spectroscopy, you have low-fidelity spectroscopy, for instance, UV-vis spectroscopy or things like that. And then, of course, you have high-throughput electrochemistry that nowadays really reaches from, the millimeter scale batteries where you can do very nice 3-electrode measurements, all the way to, lab scale manufacturing of really battery batches of 64 or even 520 cells in a single working day. And these can already translate, to this mesoscale. And this mesoscale, in terms of throughput or size, can already tell you, well, maybe that chemistry is working on the millimeter scale, but it's not yet working maybe on the centimeter or even square meter scale. And this is let's say a new link that we have for this. And for all of this, we need a couple of new tools. And this is what I try to put here on the right-hand side, is, we need the high throughput methods. There's been some development in the past, but we still need more, and BigMap was a big push for new high throughput methods. We need a digitalization of experimental research. The theorists, so Ivano's side of battery research, they are much faster than, or much further actually than we experimentalists are, because there's still a lot of work being done manual. And this is the most important thing, is we need to have integration, not just of instruments. This is where it often ends, but this is not enough. We need integration of laboratories, and we need integration of modalities. Modalities is essentially, we need integration of theory and experiment, and they need to trigger each other, and they need to be in one, let's say, sort of ether together, where they really try to push forward. And we're doing exactly that actually in BigMap. Others are trying as well, but sometimes you get a little edge. And then the really cool thing, and this is also where I think most of you actually can come into play, we also need data mining, not just with computers, because humans are pretty good in determining patterns in very complicated data. So we also need to have all these workflows together with humans, and then usually what we call this is a human in the loop kind of deal. And key to all of this is actually you need to ask not just the right questions, but you need to answer them creative, and you need to have creative question asking. So in the next slide, I just want to very briefly go on what is actually being accelerated here. So what we are aiming at is not necessarily accelerating that one instrument. In the end, I can always build a robot for you that just does things faster. I don't know. Every year there's going to be a new motor that will drive that robot a few centimeters per second faster. That's not what I'm talking about. What we are talking about is actually fundamentally changing the way how we do research. So and fundamentally changing the way how we do research means we need to actually take a step back and then really look at what are really the bottlenecks in research. What are the bottlenecks in research? If you ask the people in my lab, it's mostly, well, it's not synthesis, it's not the assembly of cells, it's actually data analysis. So then you have to, really invest in the data analysis part, for instance. And then if you go further, it's even like, okay, how do we share data with our collaborators? Well, this is another bottleneck. Sometimes it means really, you write an email and you deposit the data somewhere and, I don't know, the attachment is too large. We have to stop with that. We need to find ways of identifying these bottlenecks, preferably in user stories or whatever, and then, really look at how can we generate insights faster to then translate these insights to products. And this means that we need a new field of research, and I'd like to coin this term research engineering. That is not engineering research, where you're doing engineering, but where we engineer the very way how we do research. And if we do that, then we can, I believe, accelerate research by quite a lot. But we need really a lot of people that have all kinds of different challenges in their day-to-day work, where they say, oh, sometimes it just slows me down that, I don't know, the door opens too slow. Then you need to overcome that bottleneck. And I believe if we do that, and if we integrate laboratories, and if we integrate the modalities, not just in BigMap, but also really, that our ideas and our research is transcending the lab and the modality, then I think we can really accelerate research, not just by a factor of 10, but probably even more. And with that, I thank you for your attention, and I'm also open for any questions.
Thank you very much, Helge. Let's see, do we have questions in the room? I think we might be reaching the end of people's imagination because you've covered quite a lot there as well. And like your previous speaker, there's a lot of dense information in those slides. So if I don't see any questions, any hands being raised, I think we will leave you free to go, Helge. Thank you very much indeed. And I will remind everyone that the sessions are being recorded. So if you didn't get all the information down in that whistle-stop tour, you can go online and check it out on YouTube. Those recordings will be available in the coming days, so there's no need to miss anything. Well, that is the end of our online interactive bit. So our remaining two speakers, I am delighted to actually have in the room with us. So please welcome, a very warm welcome, please, for Isadora Sekic-Laskovic, who is from the research group leader at Helmholtz Institute in Münster.
Oh, thank you. Thank you very much. Thank you very much for the kind introduction, and I would also like to thank organizers and Christina for allowing us to present part of our results that were actually being conducted within the Big Map project. And I would like to start with the topic of my talk, and this is actually the possibilities in the domain of accelerating liquid battery electrolytes for advanced application in lithium-based batteries. And starting from the very general topic in respect to electrolytes, they're an inevitable component of each battery cell. So the battery cell cannot live with it, but living with the electrolyte can be very difficult. And this is because the electrolyte is simultaneously the key and also the Achilles heel of each battery cell, because it has a very strict role to play, and this is enabling the transport of the ions within the charge and discharge steps that are being taken place in the cell. However, there are additional requirements that each electrolyte formulation has to fulfill. And you can see here we have several different classes of electrolytes here, and you can see that actually either we are talking about solid electrolytes or liquid electrolytes or polymer electrolytes. We have been able to see yesterday and also today that we are approaching many, many challenges. And resolving certain challenges within a different class of electrolyte doesn't mean that we resolve all of them, because sadly but true, there is not a holy grail electrolyte that is suitable for each cell chemistry and application. And we really have to address the right questions: which kind of cell chemistry we want to use, and what is the application direction, because actually this will guide us to which electrolyte class is the most suitable for this job. But actually, as you know, electrolytes are being composed of several components, and in this case, if you can see here, so we have conducting salts and additives that are actually joined from many classes of electrolytes. And this is actually one of the aspects that we are trying to consider in our research as well. So we have fundamental operation and degradation processes that are taking place in the cell. And if you would like to see it, we have to separate it in 3 different levels. So at first we have to start with the material, and this means electrolyte and electrolyte components itself. Then we introduce electrolyte into the system, and then we are trying to understand the complex electrochemistry that is taking place within each cell chemistry. If we go a little bit deeper into the processes that are taking place, we can see that actually on the first side we have a chaos. We have fundamental reactions that are enabling the operation of each cell, but at the same time we are having side reactions that are actually major contributors for the failure of certain cell chemistries. And in order to advance the research, actually by developing electrolyte formulation independent whether we are talking about liquid, polymer, solid, or even hybrid, that by definition can be a combination of each of them, we simply have to tackle specific questions, and we have to try to understand the cell chemistry based on electrolyte formulation that we are using for it. So how does it look like? We learned today and yesterday also that batteries are a very complex system with a very pronounced dynamics. So in other words, this is like a proverbial search for a needle in a haystack. And the question remains: how to find the right needle for the right cell chemistry and for the right application, and not being, let's say, like a pillow for the acupuncture, meaning having several different electrolyte formulations that are more or less trade-offs for certain applications. So in other words, this would actually mean that we are struggling with optimization challenges, and that actually we have let's say, observable set, and that we are trying to find the optimum value of the observable set that is actually being a function of certain variables. And we can have 2, 3, or even more variables in this sense. So if we consider manual experimentation, there are actually 2 approaches that we can take. The first one is so-called, let's say, classical or iterative approach. And in this approach, actually, we can see here we have observable set that is actually being represented schematically here in the variable space, and dependent on variables epsilon and y and x. And you can see here that we have domains with a low value of Z and also high value of Z. And this iterative classical approach actually considers that we start from the randomized position We conduct an experiment, we try to deduce and analyze the experiment, and from the results we try to deduce which direction we have to take next. And this process is actually being repeated several times or multiple times, and in the end, actually, we can identify a maximum. So what are the good sides of this approach? Is that actually we are limited in number of experiments, which means we are just conducting several experiments, but there are also disadvantages. And those disadvantages actually comprise several different things. So the first one is actually, let's say, being trapped in a so-called local maximum, which means that we think that we have identified a maximum let's say, a value of our observable set, but in the end we are being trapped. Because anyway, if we try to go in other directions here, we will be actually trapped in the same local maximum, and we are not identifying the real optimum value of the set. And we are also dealing with sequential experiments, which means we are doing experiments one by one. And for example, if you consider galvanostatic cycling experiments, they can take weeks or months. So actually you need a lot of time. And in the end, you get just a limited knowledge gain because you're only considering a very low portion of the variable space. But there is actually a second approach, and this one is called brute force approach, in which actually you can see here we have covered the part of the chemical space in which we are trying to identify the maximum value observable set dependent on variables y and x, and we have this part of the space covered in grid, and we are characterizing it. So what are the good sides of this approach? It's easy to plan because more or less you don't need to have any kind of preliminary knowledge on your system, and more or less you get the full picture on the dependence of your observable set dependent on the variables x and y. But this approach is time extensive because there are a lot of experiments that have to be conducted, and the worst part actually is that you very easily run in a so-called combinatorial explosion, which means that number of your experiments very easily can outreach the realistic proportion. What does it mean in this simple example? For example, in this case, we have 10 points in a two-dimensional variable space. This means we have to perform 100 experiments in order to find the optimum value of the observable set. And if we add the third let's say, variable, then we are talking about 1,000 experiments that have to be performed. So now the question is, what can we do to accelerate our identification or our search for the most promising candidates, or in other words, for the observable set, dependent on the variables x and y? And this is where high-throughput experimentation comes into play, and I would try to translate it immediately into the electrolyte development and innovation. So high-throughput experimentation workflow actually has several different steps in which you have the electrolyte components that are then being combined in different concentrations and ratios. And then you have, as a result, different electrolyte formulations. Then you introduce them in different cell formats. You run high-throughput screening, or let's say high-throughput characterization. You have a, let's say, set of different requirements that you have to fulfill, and this set of requirements for each stage of high-throughput characterization actually narrow the number of possible candidates, and in the end, you are actually dealing with lead candidates for advanced cell chemistries. And this is actually schematically represented here. So you have a certain number of formulations, then you have a certain set of requirements, then you perform the measurements. All the, let's say, electrolyte formulations that fulfill certain tasks, they will be then characterized further. All that did not will be rejected. And in this filtration effect, actually, you are, let's say, being guided through the lead or hit candidate for a given cell chemistry and for a given application. But when we are talking about design of electrolytes, there are actually two approaches that we have to consider. And both are, let's say, highly being consumed in the battery community, and both are actually very valid for the identification of the promising formulations. But there are certain differences. So the first one is actually electrolyte engineering, and this is the process in which you're actually identifying your electrolyte formulations based on the performance, which means you're selecting certain physicochemical parameters for which you know will advance the performance of your electrolyte, and you're trying to vary them and try to introduce them, let's say, one by one into your cell system by varying the composition of your electrolyte, and then, of course, by let's say, the characterization and by the end of result in respect to the performance, you can actually identify the lead candidate. But you don't get any understanding there. So it means you have developed certain electrolyte for a certain cell and for a certain application, but you don't know why it works, or why it doesn't work, or how it can be improved even further. This is when electrolyte chemistry approach actually steps in or comes into play. And this is the approach that is actually driven by understanding. Because while you're developing electrolyte formulation, you're trying to understand, at first on the electrolyte component level, then on the electrolyte level, and then also on the cell level, what kind of advantages and disadvantages this electrolyte formulation actually brings into your system. And in order to do that, you actually have to bring several different methods from several different, let's say, characterization groups and try to piece all the puzzle pieces together in a way to get a complete picture on this one. And by doing this, actually, you're generating a lot of data, and we heard already how important data are. So in the first aspect, high-throughput experimentation is very beneficial because it's accelerating the way towards identifying the promising electrolyte formulation for a given battery cell chemistry and a given application. But those data can be then further used. And as schematically represented here, so we have candidate materials, which means we have different conducting salts, solvents, and additives, or conducting salts and polymer matrices, or dependent on the electrolyte class. We perform certain, let's say, amount of high-throughput experiments. Then we have the data-driven prediction. Then we have the experimental confirmation. And we have, of course, then the identification of the lead candidates. But in between, actually, we have a closed loop between the data-driven prediction and high-throughput experiments going forward and backward, and again, creating this filtration loop in order to being able to identify the promising candidates. In other words, translated, for example, for the liquid electrolytes, one of the approaches how this can be done. So you have a system, you have a salt, conducting salt, a solvent, and the additive. You have a certain set of requirements. These are the experiments that we are considering. You have a very strong synergy with theoretical simulations and computation. And then, of course, you're giving a feedback between the system, the requirements, and also the theory. And you're actually generating a library of data. And by using machine learning algorithms and, let's say, discovering certain models, you're actually fulfilling your goal, which requires pre-selection, rating and ranking, prediction and decision, and recommendation of given electrolyte components or electrolyte formulations, again, for a given cell chemistry and for a given application. And now I would just very quickly like to, let's say, emphasize what I already said on a simple example of ionic conductivity of liquid electrolyte formulations. And this is actually the system that we have developed at our institute some years ago. And among other things, and let's say the part of the system that I would like to highlight in this talk is devoted to the fully automated electrolyte formulation. And this means formulating 96 different electrolyte formulations per working day. And this is actually the end product. It's a copolymer vial with a two-dimensional data matrix where you actually have all information regarding your electrolyte formulation stored. And you can simply read all the information by your cell phone. And then we have a unified cell for conductivity measurements that was actually patented at our institute. And the beauty of this, let's say, electrode is that actually independent on the geometry of the vessel you're trying to introduce it in or the amount of the liquid electrolyte formulation, you will have no effect on the values of your conductivity measurements. And in this case, we are only using 350 microliters of electrolyte. And you can see that the cell actually is an Eppendorf. This is simply a one way, let's say, vial that you can use and trash, and it's costly affordable. So we have small blocks containing 8 of those electrodes that placed on the big rack and ending in the end in 96 different cells that can be then, let's say, put onto electrochemical impedance measurements at the same time due to the 8x12 channel multiplexer stored in the climate chamber, and we can conduct the measurements in the temperature range from -40 Celsius degrees up to 60, 80, 70, 100 or even more Celsius degrees dependent on the composition of the electrolyte formulation and the thermal stability of electrolyte components. And in the end, this is a very, let's say, simplified overview on the conductivity versus temperature curves. And all the system is being governed by the Laboratory Information Management System. It's a software that was custom developed for this purpose, where you actually store and process all input and output information. And in the end, you have also automated data processing. So in the end, you get the values of your conductivities, let's say, practically in an automated process, and all the data are being stored in a so-called JSON format, which is human and also machine-friendly format. How it looks like in the end, so this is a three-dimensional representation of the conductivity dependent on the different electrolyte components. In this case, it's a liquid electrolyte component. We have one salt, two solvents, and one additive present here. And you can see here that we have several domains in which we have high and low conductivity. We also have certain anomalies, and we also have certain crystallization effects, which means we don't have the formation of the stable solutions anymore. And these are only two temperatures, 20 and 60 degrees, and this is actually giving us a straightforward indication that the correlation between the electrolyte composition and conductivity values that we are actually determining is not as trivial as it is, and that there is a significant potential in knowledge gain if we use the right tools from the data-based analysis. And this is actually what we also did within the BigMap project. So these are the two sets of data that we generated in this way. So we had at first the conducting salt. This was lithium hexafluorophosphate. And on one side, we had a simple electrolyte formulation containing two solvents and one additive. And then you can see here that the first, let's say, model that was discovered for the prediction of the conductivity values for the liquid electrolyte formulation actually was based on a generalized Arrhenius fit using linear regression and Gaussian process regression. And you can see here, among other things that we were able to determine from the model and also use from the predictions of the model, what kind of impact the individual electrolyte components actually have on the conductivity. So here on the left side is actually impact of the conducting salt, and you can see that the model actually very accurately predicts the shift of the maximum of the conductivity in related to the concentration of the conducting salt. We see, let's say, a loose correlation in respect to the solvent impact, and what was quite surprising is actually that for vinylene carbonate, which has a quite similar structure to the solvents that we were considering this in electrolyte formulation, we were not able to see any kind of dependence. So because with this electrolyte formulation, we have experienced certain crystallization problems because we know that ethylene carbonate, which is commonly used in organic carbonates-based solvents, is stable, is solid on the room temperature and actually cause certain issues on the low temperature domain in respect to conductivity and crystallization issues. Actually, we considered introducing propylene carbonate, which is, let's say, an analog to ethylene carbonate, in the second two sets of the experimental data, actually we used two additional approaches comprising symbolic regression and also active learning, and then two additional models were developed. And as you can see here in respect to symbolic regression, actually the model shows very good predictions for the higher temperatures and, let's say, moderate concentrations and low concentrations, but there is still room for improvement for the lower temperatures and higher concentrations. So for this reason, the third approach was used, and this is a so-called one-shot active learning approach, in which you're actually discovering model that is actually suggesting you what kind of additional experiments you have to consider in order to retrain your model and refine your model, and also refine the outcomes of your model. So with these three models, actually, we could see that there is a very great potential, there is a significant potential in the knowledge gain in respect to the prediction of the conductivities, which is quite very important if you would like to introduce another electrolyte component into your system, meaning that you have a new electrolyte functional additive or a new conducting salt, and you would really like to see, well, what kind of impact then this new component has on the conductivity as one of the main physicochemical properties of the electrolyte. And now what we are doing is actually trying to refine the models and try to see in which case, which model actually is giving the best predictions. Because in this case, you don't have to run 100 or 200 experiments. You will simply do the confirmation of what the model predicted by, let's say, by this means. And this brings me to the end of my talk. So batteries are complex systems, and there are several levels that have to be considered, starting from the electrolyte level, then going to the electrolyte cell level, and actually trying to understand what kind of processes are taking place and doing it in a stepwise and a systematic approach. And instead of bringing, let's say, making a wall, we are trying to make a bridge and try to close all the gaps and bridge all the disadvantages one electrolyte formulation can bring to a certain chemistry. Learn from there, accelerate, and improve the cell chemistry. Thank you for your attention.
I'll take this one then. Okay. Thank you again. Now that people can hear me. We're going to combine our last two speakers together for questions. So if you do have questions, we'll come to them right after we hear from Simon Clark, who you can see is ready to go, research scientist at Syntef. So going to talk to us about battery ontologies for accelerated data-driven development. Over to you.
Great, thank you very much. And yeah, to start off, I'd just like to thank the organizers at the end of the day today for putting on such a nice professional event. It's been a real pleasure to be here and to listen to the other speakers as well. And you've almost made it. Last talk of the day, right? Exciting. I've been asked if I can make it a little bit lively, maybe even fun, to send us into the coffee break on a high note and a good mood, ready to continue the discussions. So, yes. I enjoy doing these kinds of talks to a little bit more general audience because it gives you the opportunity to take a step back and maybe see your own research from a slightly different perspective and learn something new. So when I was preparing, I would ask some colleagues to say, you know, what do you think is the big challenge that we need to solve in batteries in the next 5 to 10 years? And you get different answers, right? You've probably heard them today. People will tell you it's the electromaterials, or people will tell you it's the electrolyte, or the interfaces between the two. Often they tell you whatever it is that they're working on at the moment. But it got me thinking that all of those technical challenges are essential to solve, and they're very difficult to solve. But they are inherently solvable. There does exist a solution, and we will find it if we have enough time. And from my point of view, that is the big challenge and the big problem that we have to face. Can we do all of these things in the time that we have available? You know, if we consider the lithium-ion battery, it took us 50 years to go from concept to where we are today. You know, 20 years to go from concept to product, and another 30 to go from the exploding cell phones of the 90s to the slightly less exploding cell phones of today. But, you know, if we want to bring about the next generation of development, we don't have 50 years. We have maybe 8, something like that. In the solid state session this morning, we heard from the experts that they expect by 2030, maybe in your Ferrari, you can have a solid state battery. And in your Fiat, that day will eventually come somewhere down the line. It's hard to say for sure. But we do know that that day is coming. The battery market is going to become more diverse, and we have an opportunity, if we're smart, to get out ahead of it now. And if we want to do that, what do we need to do? Ultimately, we need to make efficient design decisions that are powered by powerful models and supported by abundant data. And this is kind of the secret weapon that we have in our research today that we didn't have before. So, yeah, as scientists, we kind of have this inherent obligation for acceleration, right? We always want to develop the next generation, the newest, the fastest. But in this case, we're not just doing it because it's fun or because it's interesting. It's an actual market-driven need. If we consider, just for example, the battery electric vehicle market, in the 10 years between 2010 and 2020, that market grew by an order of magnitude. And the IEA projects that by the end of this decade, it's going to grow again. You know, it end up being about 3 orders of magnitude in 20 years. And that's really incredible. I mean, it's enormous, and it's not a normal thing to be facing. And of course, this presents us with a big challenge, but it's also a great opportunity. And as battery scientists, as we look at this and we say, okay, well, you know, okay, the battery market's going to grow a lot. We need to create a lot of new batteries. But we have these lithium-ion batteries, and they work really well, right? Can't we just keep using those for everything? And it's a problem of scale, right? So if we compare the amount of materials that were consumed by the battery industry in 2019, the little blue rectangles, with what's projected to be needed by 2030, it's, you know, huge increases. And you can build a new battery gigafactory in, you know, 4 or 5 years. How long does it take to build a new nickel mine? You know, how long does it take to expand the supply chain, which now after COVID, of course, we all know is a big weakness or vulnerability that we have to be aware of. And as in any case, when there's a very high demand and a low supply, that ends up creating some interesting things with the cost. And if you remember back, you know, about a year ago, there was all these headlines coming out that you know, battery prices are going to go up. Elon Musk was in the news a lot saying, mine more nickel, and eventually actually supporting stakes in nickel mines. And yeah, over the past year, we've seen huge price increases driven partly by demand, partly by COVID, partly by conflicts around the world. And even though we've been able to steadily reduce the price of batteries over the last 10 years, how long can we, you know, keep continuing to insulate it from those costs? So, all that to say that from my point of view, it is an economic and technological and societal imperative that we develop the next generation of batteries and that we do it relatively quickly. Okay, so that sets kind of the stage for where we want to go. And I know that everybody's maybe a little bit tired at the end of the day, so I'm going to go ahead and tell you now. There's an interactive part to this presentation. So when it comes up, I'll let you know. But I will ask you a question, and you feel free to shout the answer back. It's yes or no. And if you're, you know, at home, we can't hear you, but feel free to do it anyway and startle your coworkers or something. Okay, so we need to develop the next generation of batteries. I hope that's clear. How do we do it? Well, it starts with data, right? If people are Sherlock Holmes fans, you know when he would start solving a case, sometimes he would shout, data, data, data. I cannot make bricks without clay. And as scientists, we're the same, right? We have hypotheses, we have predictions about how things will work, but ultimately, if it's not borne out in the data, it's wrong. And in some ways, we're lucky today because we have so much data available, right? I mean, we have time series battery data, we have cycling data, we have EIS, we have spectra, we have you know, images, all sorts of things. And even though we're kind of blessed with this abundance of information, it's also heterogeneous, it's difficult to work with. I'm sure everybody here has kind of faced the challenges of sending data back and forth between different research groups. And yeah, so we have all this different kind of data. It's fundamentally numbers, it's strings, it's images, and if we really break it down, it's ones and zeros, right? It's binary. And the question is, how do we translate from data to knowledge? And our kind of working hypothesis is that if you can express data in terms of binary ones and zeros, you can express knowledge in terms of triples. And a triple is a three-positional statement that's like a byte of knowledge. It expresses some little bit of information. And if you can combine them together and with enough of them, interconnected in the right ways, you start to create this great graph of information and knowledge that can be queried and reasoned over to find new information. I'll give you an example. Here it comes. All right, is everybody ready? Yeah, see everybody look up. Okay, so I'll give you an example of a triple. Simon researches batteries. Simon works at Sintef. Sintef is in Norway. Is battery research done in Norway? All right, well, we can do better than that. One more time. Is battery research done in Norway? Yes, yes it is. You know it, and the ontology also knows it. That's an example of the type of information that we can reason out about things that we put into it. But we also have to be careful, because we can make relations that may lead to false inferences. I'll give you another example. We might say humans have 2 arms, right? If in some tragic accident I were to lose one of my arms, and we said Simon only has 1 arm, is Simon human? Exactly. Yeah, it's kind of iffy. Yes, I mean, of course, we all know that I'm human. I like to think I'm still human. But the ontology doesn't. The ontology says, nope, only has 1 arm, not human. So we can, on the one hand, make these kinds of relationships that are very valuable, that can be used to make inferences, but we have to be careful to define the correct relations that we don't infer false information. So, so if we can go from data to knowledge, the next step is to go from knowledge to models. I mean, what is a model really but a mathematical quantification of some knowledge that we already have, right? We say we know particles and high concentrations will diffuse to low concentrations. Everybody here seems to be pretty well distributed, so I guess that's true. Or we know that, electric current will go down the gradient of potential. And those can be represented by Fick's law and by Ohm's law that we can then put into models to generate new data and kind of feed back into this loop. So ultimately, we can move up the steps of this pyramid, and go from data to knowledge to models and ultimately to decision making. And really, at the end of the day, that's what it takes. If we want to build new batteries, it's going to take making the correct decisions in the correct order. So let's consider if you accept that kind of premise, and you're a researcher and you sit down at your desk and you're really excited and you're ready to go and say, okay, today I'm going to accelerate battery research. You immediately run into a couple of problems. The first is data fragmentation. And it starts already at the source, right? For battery cyclers, a lot of them use their own proprietary binary formats. Different modeling softwares will export data in different formats. And if you want to make them interoperable, it usually requires somebody to sit there and either write a code to translate it automatically or have an actual physical person do it. And the result of that is that only a fraction of the data that we generate actually trickles down to the people who need it, the battery manufacturers, the engineers, the OEMs. And that's really an untapped resource if you think about all of the information that's lost, that's sitting on somebody's thumb drive somewhere, or was never put through these translation scripts. It's a real shame that we're losing all that information. The second bottleneck that we face is human expertise. Yesterday we had this great presentation from Professor Martin Winter, who went through a lot of the kind of key things that you look at for capacity fade and different degradation mechanisms in batteries. And he is able to look at some experimental data and say, oh yeah, that's lithium dendrite formation, or that's rollover failure, that's coming from crosstalk. And as a very smart person who's been in the field for a long time, he has that knowledge. But not all of us do, and not all of us have the luxury of being able to go knock on a world-leading professor's door and ask about it. So ontologies help us to address that challenge by expressing human knowledge in a machine-readable form that is able to be queried by the rest of us and used to help speed up our research. So you've heard this term a lot, ontologies, and one of the questions that I tend to get is people will say, okay, you know, I kind of get the basic gist of ontology, but what is it really? And well, it goes back a long way, all the way back to ancient Greek philosophy, where ontology is defined as the science of existence and being. Big stuff. But within the computer science industry, it really started to take off in the 1970s with artificial intelligence. And the researchers who were working on it at that time had this kind of thought experiment where they said, what if we built a robot and we wanted it to go to a restaurant and buy a salad? What information would it need in order to accomplish that? Of course, it needs to know that a restaurant is a building, that a building has an address, that it needs to move to that address, that a salad is comprised of certain things, and you'll find them at the salad bar. And you can see that even for that really simple task, the amount of knowledge that you need just explodes. And you can imagine if we want to not build a salad, but what if we want to build a better battery? You know, it really starts to expand. And ontology development took off in the 90s as a part of an effort to address that challenge. And it's been very successful in other fields in like genomics. The gene ontology database has now become the world's largest repository of knowledge for genes. And many of you use it every day in terms of Siri and you know, semantic querying helpful apps, you know, to find the nearest Italian restaurant. And you know, so it's helpful in your everyday life. But it really peaked at a moment in 1999 when Keanu Reeves was filming the movie The Matrix. And you may remember this scene. They plugged his brain into the computer and typed a few buttons, and he turns to the camera and says, "I know Kung Fu." And that's essentially what we're doing with ontology development. Whereas in The Matrix, they're uploading information from the machine to Keanu Reeves' brain. We're trying to go the other way and express knowledge in battery experts' brains in a machine-readable form that can be used to help annotate the rest of our data. And yeah, so when we create ontologies, specifically in this case, the battery interface ontology and the battery value chain ontology, we express it as a network of triples that you can kind of see here in these ovals and the arrows between them. And this provides us with two big advantages. The first is that by tagging your data to specific terms in the ontology, like cell voltage, for example, you can be sure that anything else that's tagged to that same term represents the same thing. So on the one hand, you know, it gets rid of problems like if you're collaborating with partners in Germany and everything's labeled, you know, Zeitspannungsstrom, and you don't know what that is. If it's tagged to the same identifier in the ontology, regardless of language, you get it. It also allows you to know more about the context of that information. We link to IEC standards that define certain quantities and ideas so that it provides information for the context of what it is and how it fits together. And you can encode automatically information about the units so that things are translatable. But it allows you to go a step beyond that, and if you tag two pieces of data to two terms in the ontology, you can traverse the graph and find connections between these things that may or may not have been apparent beforehand, and hopefully lead to some new insights and new knowledge about your systems. So the battery interface ontology is an ontology of electrochemistry and batteries. It was developed within the framework of the Big Map project, which the previous speakers have told us about, with the hopes of accelerating materials discovery within the battery field. And in Big Map, we're using it for a few things. Of course, common vocabularies for mapping data, creating machine-readable language, batteries and processes, supporting the interoperability of data and apps, and establishing cross-project data management plans so that, as Ivano said, he's done like a lot of really nice work curating all this, but it's 120 pages of tables. It's thousands of lines of an Excel file. Nobody wants to sit there and read through 120 tables of plain text. And by encoding it in the ontological format, you can do semantic queries to automatically get information about where the data is that you're looking for, who generated it, which project does it belong to, and maybe find some links that you were not aware of before. So it's free, open source, it's on GitHub. Feel free to follow the development. We're at the point now where we have got most of the main bits in place. The battery interface ontology is a offshoot of the EMMO, which is the elementary multi-scale materials ontology, multi-perspective materials ontology, developed by the EMMC. And this is kind of like the big overlapping ontology that's made for research throughout Europe. And a lot of this development is going on at the same time, so we have this kind of channel tunnel problem. You remember where they had to dig from France and dig from the UK at the same time and meet in the middle. But we're at that point now where we've started to meet in the middle, and our goal is to start creating demonstrators. So if you think this is interesting or could support your work or your research in some way, feel free to get in contact with me, and we'd be happy to talk about it. As a first set of demonstrators, we have three particularly that we're looking at. One is interoperability of experimental data, so time series battery data, cycle data, EIS spectra. The second is interoperability of models, that if you make a battery model in PyBAM or make a battery model in CityMod, these two can be made interoperable. And the third is to create a knowledge base for batteries that we can query to get information about them. And if we put those three things together, experimental data interoperability, model interoperability, a knowledge base about batteries, what does that kind of lead us to? A digital twin of battery systems. And that's kind of the ultimate direction that we're going, trying to create semantically described digital twins that allow you to link physical assets to their experimental data, to models that predict their performance, and to a battery knowledge base that allows you to make queries about what its performance will be under different conditions. So, to summarize, within BigMap, we're developing ontologies for batteries, and this is part of a larger European initiative on ontologies generally, not just for materials discovery and lab stuff like we're working on in BigMap, but also for battery value chain, manufacturing, and so on. This will be used to generate knowledge graphs that people can use to make semantic queries to try to find out more about their data and their systems. We hope that this will support semantic interoperability among battery data sources and modeling frameworks. And ultimately, we want to remove the human bottlenecks in these processes and try to automate the setup, running, post-processing of physical and virtual experiments. And my eyes aren't as good as they used to be, and I can't read that, so I'm going to turn around and say dramatic reduction in time and cost of development, improved lifetime and safety. So thank you very much for your attention, and yeah, happy to discuss more in the panel.
Well, thank you very much indeed. Now, I don't see any online questions, but I did notice that there was a hand raised here. I think it was a question for Isidora. And we'll take any questions you might have for Simon now as well. So if you could introduce yourself and briefly explain your question.
Can you hear me? Okay. My name is Yiğit. I'm from Aselsan, Turkey. I want to ask this question for better understanding. So you are using artificial intelligence and machine learning algorithms to get a model, right? Mathematical model, digital model. Am I right? So you need to optimize this model, this mathematical model also. This is right also. Can you understand?
So it's not just a mathematical model. This is also a physics-based model, because you have to introduce certain laws that are being followed. Just given an example of conductivity, in order to discover the model at first that would give you good predictions. And let's say the main idea of this model actually is to try to accelerate the identification of certain electrolyte formulations in a way. For standard electrolyte formulations, you more or less know where the conductivity, in which range conductivity is. But for example, you have synthesized a new salt, and you want to introduce it into formulation. So just the presence of the salt doesn't mean that you have found the optimum one.
I understand.
Yes, you need to find the optimum concentration, which means the model could give you a prediction what would be the optimum concentration of this salt for this electrolyte formulation.
You use another machine learning or something else like that, genetic algorithms for optimization for this model?
Yes.
Some kind of genetic algorithm?
Yes, and I have shown that it is not only one model, there are several different models, and actually what we are trying to do now is to organize a so-called platform in which you could choose which model, so you can try to introduce your desired electrolyte formulation, and you can see which of those models is actually the best solution or which one will give you the best prediction for the given conditions or for the given formulation.
Okay, thank you.
Thank you very much. Any questions for our... Yes, we have another hand raised at the back.
Hi, so my name is Nicolas von Drachenfels. I'm from the Battery Lab Factory in Braunschweig in Germany. My question is directed to Simon. Basically, I have two questions. So the first one is, you showed the battery interface ontology, but you also mentioned that you have a battery value chain ontology. I guess they should meet at some point, maybe in the production. So maybe you can explain how at some point those ontologies will meet and how you stop it from ending up in a world model. And the second question is to your numbers that you showed in the beginning. You said the Human Genome Project took about 20 or even more years to finish. Now we only have 8 years. So the question is, how long do you think will it take to have like a really good working ontology that we can use?
Yep, thanks for your question. So to the first one, when we do ontology development, we try to adhere to some common standards so that people working on one domain and people working on another domain can use them interchangeably. Otherwise, it just becomes, crazy, the amount of things you have to describe. So within BigMap and the battery interface ontology, we're focused on electrochemistry and battery cells. And then the battery value chain ontology, which is being driven by Fraunhofer ISC in Germany, is focused on battery manufacturing, recycling, and the larger scale things. So the battery value chain ontology, BVCO, imports BAT-info for its description of battery cells and builds on top of it for the descriptions of manufacturing processes. So we work together really closely, and they're already integrated. And if you're interested in that, I can recommend, give them some shout-outs for some of their projects. They have one that I think is really cool called KI Probat, and they have a nice website. You can Google it. And that's a really nice example of how ontologies can be used to help gain information in the battery manufacturing domain. And your second question was on how long will it take? Yes. So we have the first version of the battery interface ontology available now, and we're starting to move into creating demonstrators, and that's where a lot of the devil is in the details, so I think a lot of the challenges will come out there. But our goal is to have some demonstrators ready by the end of this year. We're already starting to work on some, and we'll publish a paper on a practical guideline for generating fair battery data in the research field. And our goal is to have it completed with demonstrators moving towards this digital twin concept by 1 year from now.
Any other questions? I see several hands on this side of the room. So if we can get a microphone over there. Thank you.
Thank you. My name is Evelina Castellana from Lobartov, an environmental engineering SME. And my question borns out of curiosity. Maybe it's a little bit far from your research topic, but it's something that has been highlighted during the past session, is the importance of sustainability requirements. So I was wondering if within your projects, if it is something that is considered also within the alignment of the digitalization of the battery development, and if yes, how is this considered? Thank you.
It's a very complex and difficult approach to take. because you have to consider several different levels in your battery cell. So regarding sustainability, if you're talking about the electrolyte, you need all the requirements for certain electrolyte formulation that it has to be fulfilled. But also on the other side, you have to go to the other requirements and to see how they compete with sustainability. And you have to find a trade-off at first on the electrolyte level. When you introduce electrolyte to your cell, you have to do the same thing. So in the end, it will be a trade-off. Because in a certain way, you will win certain things, but certain things will be then lost.
Okay, we had another question, I think, right here.
Yes, Tuğrul Çetinkaya from Sakarya University in Turkey. My question is about, I think in your process, the collecting the experimental data is very important. So how you are sure that the experimental data is confidential? Because you know that, for example, when I say my two students they follow the same experimental procedure, they can give me two different results. I mean, just how you manage to put there the correct experimental data.
Is that question for Simon or for Isidore?
I think we can both.
I think you can both tackle that one.
And so were you talking about the confidentiality of data or the correctness?
Experimental data that you are collecting the experimental data and then you are putting there on the table, and how you are sure that your experimental data is true.
Okay, well, I kind of see those as two things. One is confidentiality.
Yes, how you manage that? Do you make some cross-check, or because just if you repeat that test only one time, maybe it may be wrong?
Yeah, exactly. But that's kind of an interesting thing that we also talked about yesterday in the Battery 2030 meeting, is that all data is valuable, even wrong data. And you know, knowledge about failed experiments and knowledge about things gone wrong is also of value to the community. So within the infrastructure that we're working on, we're trying to make avenues that you can express that. And yeah, that's kind of my perspective on it. But maybe I'm not an experimentalist, so maybe.
And then coming back to the experimental side, of course, you never run your experiment only one time. And to be sure that you're actually getting accurate results, not only precise, but also accurate, actually you make several repetitions. And what we do, for example, for certain measurement, we even do up to 10 repetitions. So actually, in the end, you will have outliers. The outliers will be then excluded from the analysis. And then if needed, certain experiments will be then again repeated in order to get highly reproducible data.
Okay, we had another question here, please.
Hello, Thomas Schmalz from the Fraunhofer Institute for System and Innovation Research in Karlsruhe, Germany. I very much like the idea of open science, and thank you very much for your presentations. I find it very insightful. I was just wondering, we were discussing earlier today that in Europe we're actually quite good on the R&D level in battery science. But how, at the same time in the EU we have a bit a problem to translate really to IP and to make companies out of it, basically. And so I was just wondering how this concept of open science, of data sharing, how do we bring this together to actually create IP out of that?
Simon, I think, perhaps.
Yep. Yeah, that's a really good question, and it's kind of a double-edged sword that we're trying to navigate. On the one hand, and we had a panel about this with Stefano Pastorini last week, who had some interesting insights on it. But a lot, it's happened time and again, right? That for lithium-ion batteries, a lot of the early research was done in Europe, and it's commercialized in China. For sodium-ion batteries, the same thing. I'm originally from the United States, and even though we don't invest so much in battery research, we do a very good job of commercializing things. And this is venturing into the realm of opinion, but in my opinion, it's because in the United States we have a much more startup-driven culture. You know, Calvin Coolidge famously said, "The business of America is business," and that really factors into to all of our research infrastructures and endeavors. On the other hand, you know, it's a huge challenge that we face, and no one person can do it alone. No one company can do it alone. If we're going to be successful in meeting these kinds of grand challenges, we have to collaborate. And in my way of thinking, I think that sharing data, especially from a company's point of view, while of course, you know, you have to protect confidentiality and you have to protect IP, there are ways to make it more of an asset to the company's business plan than a risk, you know, that somebody's going to steal all of your information. And by being proactive about that, I think we can yeah, try to walk that line. But it's really difficult. I know that's probably not the greatest answer in the world, but it's something I'm also making a lot of thoughts about and trying to figure out.
It's also not something that's unique to this sector in terms of open data and data sharing and IP. Any other questions? Yes, just one here, and I think that's probably the last.
Yes, thank you. Wouter IJzermans from the BEPA, Battery European Partnership Association. So we are advising the European Union what to put in their calls, tenders for new grants, new projects. Of course, when I see this like open ontology is really good, and we want to maybe encourage that and say to our projects, you should contribute to the knowledge that you gather, put this into this ontology. How do you look at that? To what extent is it a burden for researchers to go through the process to upload it in here as well, compared to the gain that we can overall get as a science community? So how do you feel about the individual project versus the database?
Yeah, that's a really good question, and it's like with any kind of development or any kind of tool. If it's not easy, people won't use it. And so we're really trying over the next year to make some tools and trainings that show people the value of using it and the ease with which it can be done. And you know, if we compare it with the way of doing data management now, you know, as part of research projects, we have to create these documents with these tables. Ivano kind of went through that, and you know, it's hundreds of pages, you know, huge amounts of tables, and that in and of itself is a big effort. Yeah, all that to say that you know, we're working on ways to make it easy. We're trying to demonstrate the value, that this is not just something that you have to do to check a box, but it's something that actually, you know, helps you in your research. And I hope we can demonstrate that.
Isidore, any final policy call, not necessarily on this topic, but any wrap-up comment from you?
I think one has to keep being motivated, and I think the key to success is actually related to asking yourself the right question, to try to tackle the problem from one specific point, and then to try to follow further directions in order to explore all the possibilities. And by understanding certain things, one can then improve himself or herself, and then simply go forward with the research.
Well, thank you both very much indeed. A round of applause for both our presenters this afternoon. So, a little bit earlier than planned. I'm sure everyone will be happy to stretch their legs and get to the cocktail. But first of all, I have a little bit of housekeeping. Tomorrow we start again. The registration will be open from 8:30, but please do keep your badges from today. You can use those again. But if you want to come and start networking early, there will be a welcome breakfast from 8:30. For those joining online, remember the exhibitors' booths are still open. You can go there and interact on the platform. Once again, the hashtags for social media to tell everyone what a great day you had today. They are BAT for EU, BID or BID or BID 2022. Remember to follow those for updates on what's going on online. And with that, I will allow you all to make your way through to the Riverside area for some final networking and a cocktail reception. So thank you all. Bring your thinking hats tomorrow morning.